thanks for inviting me, and nice meeting you all. I know some of you, not everybody, and so it's nice actually to enter more and more in this community. I will start my presentation right away because I'm having some problems with the internet connection. So I hope that everything goes smoothly, but let's move on, just for being safe. So my name is Antonio Rinaldi. I trust that you see my screen just fine. I'm the project coordinator of NEXTOWER. And NEXTOWER is a project on CSP, but from the NEXTOWER is advanced material solutions for generation, high efficiency, concentrated solar power tower systems. This is an action that is coming to an end. Of course, we are entering into the last semester. We got an extension, but we are fully, deeply involved into prototype validation and to looking at wrapping up all we have done so far. It has been a very long journey. I'll try to give you, as was in the abstract, a little bit of an overview of where we are, what were the lesson that we learned, and we can share with you. Of course, I'm presenting here on behalf of the entire consortium and all partners, giving credits to everybody. So, as far as the scope is, we are focusing on type of CSP, and out of this, we actually focused on a couple of aspects where we actually identified some bottlenecks from the material standpoint. Of course, what the European community is asking us is, of course, to increase the performance of materials in terms of expected service life, as well as higher working temperature range. So we try to address this, trying to move away and look at what can be done to move to another generation of CSP system and moving away from molten salt type of storage technology, for instance, and having ceramic receivers that are able to withstand better extreme thermal gradients, and so have better performance in terms of durability and toughness to thermal shocks. So these are the blocks that we try to develop materials for. So we look at the receiver upstream. Then we actually look at thermal storage, trying to actually consider liquid lead type of new system, and also try to see whether we could interface this directly with gas turbines. And to do that, we have to raise the working temperature of our cycle well above what they are currently. Try to reach 800, 900. Then we start looking at the possibility of interfacing with gas turbines. So as far as the solar receivers we are developing and we are testing at this stage, these are the ones that are mounted, that were mounted at on the CISA tower at PSA-CIEMAT, which is one of our main partner in the consortium, and is responsible for the first type of prototype. And in that case, we are improving the performance of the. Okay, I'll come later. Probably there was a slide that ended up a little later. So we are focusing on delivering tiles and caps created with a better technology from NGSER and LICTEC. These are the same partners who have been participating in the creation of the very first ceramic receivers that were mounted on CISA 1 tower more than 10 years ago. And now they improved on their manufacturing process. So as a result, we have a better ceramics that can better withstand thermal gradients. Just some project details. I'm not going to stop here a lot because these are publicly available. You can go on our website and get all this type of information to see exactly also who is participating. Again, this was supposed actually to be before the ceramics. So this is the scope of the project. We are essentially focusing on the new receiver. And then we are trying to say if we are now able to have a receiver that works at much higher temperature, how can we couple this, let's say, hotter fluid, thermal fluid exchange? We are trying to explore, drawing directly to the nuclear experience that ENEA has, is to use liquid lead or liquid metal for the metals for the storage block. Anything that is below, okay, the storage block is out of the scope of the present project, but can be undertaken, of course, in a subsequent follow-up project. Of course, interfacing with gas turbine and how to use industrial heat when you have this high quality heat available, of course, for processing. And I have to say that ETN, the European Turbine Network, is actually one of our trusted subcontractor, providing some insight in this respect, even though it's not a core activity of the project. This is the consortium as a whole. We are not picturing here subcontractors, but we do have relevant subcontractors. We have ETN, the European Turbine Network. We have CEA in France doing some relevant modeling for the calculation of the levelized cost of electricity for our system. And then we also have CENER, who will present later and has performed some studies in terms of possible application of a beam down architecture coupled with some of the ideas that we have explored in NEXTOWER. And there is also CNR from Italy. So right now we are looking at a prototype demonstration that has two parts. One is dealing with ceramics, advanced engineering tests 3 years, and now they have been produced and mounted on, or being mounted in Spain to undergo actually a real cycling in standard conditions and accelerated cycling in the solar furnace. On the other hand, we are trying to set up and test, COVID allowing, our new materials and the new architecture for the liquid lead storage block being tested in Italy instead. So essentially the SOLED prototype, SOLED is the name of this prototype, is actually split in these two parts and it's been tested in Spain and in Italy. We were unable to actually create one unique prototype combining the solar receiving part and the storage block in one site. So what are the clear in mind? We have the durability of monolithic ceramic materials for the volumetric type receivers that have been already used historically on atmospheric type tower system, and to create a new generation of storage, energy storage system based on liquid lead. And of course, to do that, you need to create really an enabling material that would withstand liquid metal corrosion that above 600 becomes a serious problem. Standard steels, when in contact with stainless steel and or carbon steels, when in contact with liquid lead, suffer from extreme corrosion problem from liquid metal attack that is essentially leaches out the nickel, okay? So we developed together with Sandvik, who is another important partner in our consortium, brand new materials and a new type of design where we have a special alloy protecting from liquid metal corrosion and self-healing under the action of a high temperature liquid lead, placed on top of a super alloy that guarantees the structural function. A little bit as a close-up, let me show you what are the deliverables of our project, okay? So we have engineered a little bit the lattice of a foam that is going now to be deployed in actual testing. We have worked out on the joining techniques. We have used the actual geometry of the caps because we have produced the caps that are now being installed in Spain. How are they going to work, we will tell you in a few months. We trust from our experiments that there has been a significant improvement with respect to the prior generation receiver. We have optimized the lattice for thermofluid performance and heat exchange. So our lattices are, based on laboratory experiments, more performing than the prior generation. Let's see now how durable they are. So if they can withstand the test of time. The second type of deliverable I want to show you is this single chamber storage block with two heat exchangers, a primary and a secondary, that are in the same chamber, where we rely on natural, actually, on convection of liquid lead inside this chamber, exchanging, heat from one side or another, depending on whether we are loading or discharging the storage block between the two heat exchangers. Okay, so this is a design that is created entirely to ENEA as a concept, has been engineered by CALEF, which is our industrial consortium that works as a contractor for engineering for this project. And we have Walter Tosto, another renowned producer in Italy, to produce actually this component by overlay welding. We are talking about more than 10 kilometers of wire applied as overlay welded cladding onto a structural steel, and highly complex geometry that is being produced between Walter Tosto and Sandvik. So from a manufacturing standpoint, I'm very proud of my team, and I have to commend their work, because they are being extraordinary. So this is a batch of material that we were able to produce, and in large batches, so up to several tons per batch. Sandvik really put all its effort into this project, and they have made a fantastic series of batches, experimental batches, and scaling up work that everybody's pretty happy with. So this is to make these innovations readily available for other projects, subsequent projects, and also ready for the market, as long as we are able to dive into a proper standardization type of activity, so that these materials get a little bit tested by more broadly and accepted also for other application by the larger industrial community. These materials, for instance, can be used, they are FeCrAl material, they contain a certain quantity of aluminum that is able to produce an alumina forming protective layer that stops corrosion and attacks from a harsh environment, also for CO2, for instance. So this supercritical CO2 is one of the applications that could be benefiting from this type of innovation that we are bringing from NEXTOWER. These are some of the tests that we have been doing. In this picture here, if you can see it, there is a very thin layer of alumina that is from top, because we have to produce the material in terms of casted alloy, and then we have, of course, to produce it in terms of strips and wires, and to characterize it as welded, which is, of course, a challenge, because we have to control, to ensure the intended design objective, that the content of nickel on each pass is controlled. So this has been a lot of work. Again, this is going to be tested in our facility in Italy. Brasimone is being installed these days. We are going to start melting and conditioning the liquid lead probably during November. And then when the liquid lead is properly conditioned, controlled from a chemical standpoint, oxygen content, and is ready, then we will load the main vessel, and we'll start cycling the main vessel as much as we can, compatibly with the duration of the project and compatibly with COVID, if we don't get another lockdown. In terms of impact, is broad. I mean, materials can really be applied, especially the steel that we have, the alloys, the metallic alloys we have produced, can really be applied in steam and gas turbine, chemical industry, and can really be used to reinforce what increase the durability of components under harsh conditions in general. Applications are being evaluated by our exploitation team and will be conveyed in a specific deliverable to the European Commission, and probably some of this will be made available to everybody, trying to see how in each sector we can apply the technology that we brought through our research. Again, I would like to say, to show this idea, because we do believe that the liquid lead technology could have a future, see all the weight that is involved in this. In a beam down type of concept, we will see whether we can exploit it or not in another project. But you have to think that the vessel that I showed you, which is 3 meters high, 1 meter across, when it's filled with liquid lead, it weighs more than 45 tons. Just the lead accounts for about 32 tons. So this was one of the problems. In the end, we decided not to risk to lift this up in the air, but we do believe that it needs to stay on the ground. I would like to say one thing. We have been engaging as much as possible with standardization. UNE is the standardization body of Spain, is a partner, and has looked at task force that systematically reviewed all our results from ceramics and from metallic and liquid lead part. What was done and what was mature enough allowed us to actually contribute to ISO and Sensenelec standards, which in the end allowed us to our surprise indeed, to win, to receive the Innovation and Standardization Award 2020 from Sensenelec, which was awarded in September. So again, this is a result that is certainly to be credited to the incredible work that the entire team, 18 partners, have done over the past basically 4 years. This is the ritual acknowledgement of the European Commission, who provided us with the funding necessary to carry out this work. And of course, I'd like to thank you for your attention, and I'll be most glad to get in touch with you to answer your question if I can, or now or later on offline. Thank you.